So, in the last week, we started to understand what it means to do to formalize a reinforcement learning problem using a Markov decision process. But we didn't really talk about how to solve those Markov decision processes. So today and for the rest of the course, essentially, we're going to start to talk about solution methods. So we're going to start to look on the agent side, how to build things that can actually solve these problems. And one of the fundamental building blocks, perhaps the most fundamental and oldest idea behind not just reinforcement learning, but control, optimal control, is the idea of dynamic programming and planning by dynamic programming. So that's today's lecture. We're going to start by introducing it, understanding what the idea is, what it means, and we're going to talk about three basic fundamental paradigms to which dynamic programming can be applied. First of all, we're going to consider the problem of policy evaluation, which is if someone gives you a policy, how good is that policy? If I wander around randomly, how much reward am I going to collect in that MDP? Then we're going to see how we can use that solution method that we've come up with to evaluate how much reward we're going to get to build our first overall solution method that can find the optimal policy for an MDP. And that's policy iteration, which basically takes this idea of evaluating policy as an inner loop and loops around making our policy better and better and better until we find the best possible, the maximum amount of reward we can get from that MDP. And then we're going to talk about another approach, very related, called value iteration, which works directly on value functions and doesn't work in policy space, but works directly to make the value function better and better and better by applying the Bellman equation iteratively until we actually arrive at the optimal solution to the MDP. Then, time allowing, we'll talk about some extensions to dynamic programming, which lead to a wide variety of different ideas, leading into the subsequent lectures where we'll actually pull out lots of the core ideas of policy evaluation, policy iteration, value iteration, and we'll turn them into more general reinforcement learning methods. So what's the distinction? Why are we talking about planning today and reinforcement learning tomorrow? Remember, these are different problem settings, and we'll discuss that in just a second. And finally, this may just be something for the notes, depending on how much time we have, but I'd like to at least give you some intuition as to why these methods work. So just the maths behind that. That's the only kind of formal section, really. It's just make you understand why it is that these things find a solution and that that solution's unique and the right thing to do in the MDP. Okay, so let's start with a brief introduction. So first of all, what is dynamic programming? Why is it even called dynamic programming? Well, first of all, we have the word dynamic, which basically means that we're considering problems that have some kind of sequential or temporal aspect to the problem. So problems which have step by step, something changes, and we're trying to solve this problem in some stepwise fashion. And secondly, the word programming, we don't mean programming like writing a C program or JavaScript or something. We're talking about mathematical programming in the same sense of linear programming or quadratic programming. And that really means optimizing a program, where mathematicians, by program, what they mean is essentially what we would refer to as a policy. You start off with some mapping from states to actions in our case, and you optimize that program for behavior. So dynamic programming puts these two ideas together, so it's an optimization method for sequential problems. I'm not sure why the color is going in the projector. Oh, well, I'll just add a bit of kind of psychedelic flavor to everything we talk about. Okay. So, at its heart, dynamic programming lets us solve complex problems by doing two things. It basically breaks them down into subproblems, and then it puts those subproblems back together to solve the overall solution. Okay? So any problem that we can break down into subproblems and then solve for each of those subproblems, put them back together, is the situation where dynamic programming can excel. Specifically, dynamic programming needs to have two properties in order to be applicable. This is not about RL yet. This is just the general idea of dynamic programming. So you need to have something called optimal substructure, which basically means that this thing called the principle of optimality applies, which we'll talk about later. But optimal substructure basically tells you that you can solve some overall problem by breaking it down into two pieces, or more than two or more pieces, solving for each of those pieces, and that the optimal solution to those pieces tells you how to get the optimal solution to your overall problem. Okay? So if that didn't apply, it would be useless to first of all solve the subproblems, because by solving the subproblems, you haven't made progress towards your overall problem. So the canonical example is the shortest path. The shortest path from here to that wall, I can break it down into some midpoint, and I can say the shortest path to the wall is the shortest path to that midpoint combined with the shortest path from the midpoint to the wall. Okay, that's an example of optimal substructure with a principle of optimality. And so this basically tells us that we can take our optimal solution and we can decompose it. We can start working with these little fragments, solve for these smaller problems first, divide and conquer. We can break things down into simpler pieces, solve for those simpler pieces, and then put them back together again. The second property we require is called overlapping subproblems. So what does this mean? Well, this means that the subproblems which occur again and again and again. Like that actually we've got something to gain by breaking it down into subproblems, that by solving that subproblem, we actually can solve things more efficiently than we could have by just attacking the overall problem directly. And basically all we require is that the subproblems kind of recur many times. That, in other words, if I break down the problem of getting to that wall into first of all going to the midpoint and then going to the wall, that also helps me solve. Now I've solved the subproblem of the shortest path from here to the wall. That also helps me solve the subproblem of how to get from here to the wall, because I can go to that same midpoint and then still get to the wall in the most efficient way. So the same subproblem has occurred for many higher level problems that I want to solve. So those subproblems recur many times, and that means we can cache our solutions to those subproblems and reuse them and get an overall efficient divide and conquer approach. So how does this apply to us? Well, we're talking about Markov decision processes today, and we're going to try and solve them using dynamic programming. And luckily, MDPs satisfy both of these properties. And the special properties which MDPs have are basically the Bellman equation. The Bellman equation that we saw last week is the recursive decomposition that gives us these properties that we're after. So the Bellman equation told us last week, if you recall, how to break down the optimal value function into two pieces. The optimal behavior for one step, followed by the optimal behavior after that step. That's what the Bellman equation was telling us, that you can understand the overall value, the optimal value from any state, in terms of doing the best thing for one step and then the best thing for the remainder of your trajectory. Okay? So that's what the Bellman equation gives us, this recursive decomposition. And the thing which gives us overlapping subproblems, this caching and reuse, is the value function. The value function, you can think of a value function as something which is like a cache of all the good information we figured out about the MDP. The value function is something that says for any state, I've already figured out what the solution is from that state onwards. The value function tells you the optimal way to behave, the optimal value, the maximum reward you can get from that state onwards. Once you've got that, you can kind of work your way backwards. It's like saying, once I've already figured out the optimal path from here to the wall, I could just store that thing, call that V of S for this state S, and now I can remember that. And now if I ever want to work out anything which relies on that V of S, I've already cached that information. I don't need to recompute it. I don't need to do like a full tree search into the future over all possible paths. That information is stored, it's cached in the value function. And this is why value functions are such a central and important idea for reinforcement learning. Okay, so that's dynamic programming in a nutshell. So this is a very, very kind of 1,000-mile overview of dynamic programming, no details yet. So what we're going to do specifically is we're going to try and plan by dynamic programming. So if you remember the definitions of planning, planning is this problem. It's not the full reinforcement learning problem. It's a different problem where someone tells us the structure of the MDP. Someone tells us the dynamics and the reward for that MDP, and now we want to solve that MDP given full perfect knowledge of how the environment works. It's not the full reinforcement learning problem. So we're not going to address that today. We're just going to address the planning problem. So someone tells us the transition structure, someone tells us the reward structure. Now how do we figure out the answer to this MDP? How do we solve it? And we can solve two special cases of planning in an MDP. We can solve, and again, this came up in the introduction, this idea of prediction and control. So first of all, we can plan to solve the prediction problem. So what does that mean? Well, it means that someone tells us an MDP. So someone tells us that, remember, an MDP is like a state space, an action space, our transition dynamics, our reward function, and a discount factor. It's just our standard MDP. So someone tells us the MDP, but they also give us a policy. They say, for example, if you're going to wander around randomly in this world, then what I want to know is how much reward will you get in that world? And this could also be a Markov reward process. But the output of this process, so what we're asking for, is some black box that is this planning thing, which you give it the MDP, and you give it a policy, and it tells you a value function. The output is a value function of the planner. The value function tells you how much reward you're going to get from any state in this MDP. And so that's what we want to do for the prediction case. That's the first form of planning that we might consider. So this is policy evaluation, figuring out how good a policy is. How much reward are we going to get when we wander around in this world? The second type of planning we're going to consider is control. This is the full optimization, when we're really trying to figure out the best thing to do in the MDP. But again, we're just considering the planning case. Someone tells us the MDP. This thing is known. It's like we're given if you remember the Atari example, it's like someone gives us all the details of the Atari game that we're going to play. We're given access to the internals of how the next state is produced. And we're going to try and do control. So someone gives us an MDP. But now, instead of giving us a policy, what they want to know is the best policy. They want to know, amongst all different policies, what's the most reward that can be achieved in this MDP. So informally, this is what we think of when we think about solving an MDP. We think about this guy. We want to kind of know what's the best thing that you can do in this MDP. What's the most reward that can be achieved? What's the best possible policy, the best mapping from states to actions that is going to achieve the most long-term reward in this MDP? And so that's the problem we're going to address later on. So we'll start with prediction, figuring out how to work out how much reward you'll get under a given policy, and then we'll use that as an inner loop to do control. Okay. Sorry, and I should have said, in addition to outputting the optimal value function, when we do control, the thing we ultimately care about is the policy. We want to know how to behave. What's the action that will give us the most reward in every situation? For every state, tell me the best action that you can take. And that is the optimal policy. And this implies this, as we saw in the last lecture. So when we do control, we pass in an MDP, we get back optimal value function, or equivalently, the optimal policy. Okay, so dynamic programming is very widely used. There's lots of places it gets used. So I just want to not leave you with this sense that dynamic programming is only used for planning and MDPs. It's used in scheduling algorithms. It's used in string algorithms for like sequence alignment problems, very popular in bioinformatics. It's used for graph algorithms. Like if you think of shortest path algorithms, these are essentially dynamic programming algorithms. If you think about graphical models in other machine learning, like we've been doing supervised learning, the Viterbi algorithm is an example of dynamic programming. Lattice models in bioinformatics again. Anything where you've got some kind of structure like a lattice or a string or a shortest path where there's this optimal substructure and the principle of optimality. And then you can put these things together, efficiently solve the subproblems, figure out something about the overall problem. Okay, but we're not going to talk about these today. We're going to focus on MDPs. Just want you to be aware that that's not what everyone means when they talk about dynamic programming. Okay, so let's start with the first key component, which is trying to evaluate a given policy. So this is that case. Someone tells you the MDP. They tell you the policy. Now, I'm going to wander around this policy. I'm always going to go straight ahead. How much reward am I going to get? And then we'll move on, and we'll see how that helps us make progress towards the problem we really care about, which is maximizing reward. Okay, so here we are. We want to evaluate this policy. And how are we going to do it? We're going to use the Bellman equation that we saw last week. So in particular, if you recall, last week we had different flavors of Bellman equation. We had the Bellman expectation equation, and we had the Bellman optimality equation. And what we're going to see is that we use the Bellman expectation equation to do policy evaluation, and we use the Bellman optimality equation later to do control. So each one is applied to solve a different type of problem. But what we're going to do is take that Bellman equation and turn it into an iterative update. And that's going to give us our mechanism, our first mechanism, not the only mechanism we'll see, our first mechanism for evaluating policies. So what we're going to do is essentially we're going to start off with some arbitrary initial value function, v1. So v1 you can think of as just like a vector of, so this thing is basically telling us what's the value of all states in the MDP. And we're going to start off with some arbitrary initial value. So 0 would be the canonical case. We start off thinking I can't get any reward anywhere. And then what we're going to do is we're going to plug in our one step of our Bellman equation. We're going to do that one step look ahead using our Bellman equation. And we're going to figure out the value, a new value function, which we're going to call v2. And we're going to iterate this process many times. And at the end of this, what we're going to see is that the thing which we end up with is actually the true value function. There's a few more spaces, by the way, just scattered around. It doesn't look so great over there. And the way we're going to do this is using what we call synchronous backups. We'll see the alternative later on when we get to later slides. So what do we mean by synchronous backups? What we mean is that every single iteration, what we're going to do is every iteration, we're going to consider all states in our MDP So we're going to sweep over all states in one iteration. So what we're going to do is we're going to start off with our previous value function, and we're going to apply our iterative update to every single state in this value function to produce a complete new value function for all states. And then we're going to look at every state in this value function. We're going to apply a complete new update to give us a new value function. That's called synchronous evaluation. We consider all states at every step. And we'll consider asynchronous backups later, which can be more effective. But this is the simplest case. Okay. And don't worry about convergence yet. We'll see later on. I'm going to defer the question of convergence. So you just have to trust me for now that this process that we'll see really does converge to the true value for each of the states. So let's understand exactly what we're doing. What actually is the update? So all we're going to do is we're going to take our Bellman equation that we had before. So if you remember, this was our look-ahead tree that kind of showed us how to compute the value function. This was the Bellman expectation backup, so-called expectation, because we've got an expectation over our actions rather than a max over our actions. That gave us, the max gave us the optimality equation, the expectation gives us the Bellman expectation equation. And this was the vector form of the same thing. But just intuitively, I like to think of it as just a one-step look ahead. That we look ahead, the value of the root, and this is just the Bellman equation for now, the value of the root is given by a one-step look ahead, where we consider all the actions we might take. This is the things I might do as an agent, and then all the places the wind might blow me. And then we look at the value of these successor states that we might end up in, and we back that all up, we sum it all together weighted by the probabilities of each leaf, and that gives us our root value, the value function of the root. So all we're going to do with dynamic programming is we're going to take this equality, so the Bellman equation told us this thing must be true for the true value function v pi. That tells us that this must be equal to this. And now all we're going to do for dynamic programming is we're going to turn this equation into an iterative update. In other words, we're going to define the value function at the next iteration by plugging in the previous iteration's values at the leaves. So we basically take our value function from the last iteration, vk, we plug in those values that we had at the leaves, we back up those values to compute one single new value for the next iteration at the root. So we figure out vk plus 1s by doing a one-step look ahead, looking up our values here from our last value function, and now we fill in, we've got one state, and we're going to do this for every single state. Every single state in our sweep, in our synchronous evaluation of dynamic programming, every single state gets a turn at being the root. And so they all get one of these updates. We do this for every single state in the MDP, and we figure out the new value of that state at the next iteration, and that gives us a complete new value function. Okay, that's the idea of iterative policy evaluation. And then what we do is we iterate that process. We iterate that process, we take the value function we've just computed, our vk plus 1 that we've just computed, and now that will take a turn at being the leaf. We plug that in at the leaves, we back that up, and we would get vk plus 2 at the root. We do that for every state, we iterate, and this process is guaranteed to converge on the true value function. Yeah, question?
What happens that there won't exist any vector v that would satisfy the equation?
Another vector v?
No. That, there won't be any vector v that would satisfy the equation.
Is the question, how do we know that there is the existence of a v that satisfies this equation? Yeah, well, I'll come back to that at the end of the talk, if you don't mind. So there's a formal proof that I'll at least try to illustrate at the end of the class. So for now, there always is. So it comes from the uniqueness property of the solution of the MDP, which we touched on last time. There was a theorem in the last lecture that said for any MDP, we were talking about v star there, the same is true for v pi. But there is a unique value function that satisfies this for any MDP. And we'll see why later. It's essentially a contraction mapping theorem. It's the easiest way to see it. Okay. Is that clear for now? Let's do an example. I think that will help. Right. Okay, so we'll consider this very simple example. Okay, so we're going to consider this. This is a small grid world. So what's this grid world about? So we've basically just got this little 4x4 grid. It's got two shaded states in the corner here. These are terminal states. If you end up in this state, end of episode, no more reward. Or equivalently, you can think of this, you just end up going round and round and round, getting 0 rewards forever. Same thing. Okay. Now, what happens elsewhere is that you've got 4 actions that you can choose, north, east, south, or west, 4 compass directions. If you take an action that would take you off the grid, it just has no effect and you remain there. Okay, that's the definition of these grid world examples. We'll see more later on as well. And we're going to get a reward of -1 per step, regardless of which action you take. So if you go north, east, south, or west, you're going to get -1, regardless of whether it take you off or not. You're just going to get -1 per step. And the only thing which differentiates how much reward you get is when eventually you get to the terminal state, you stop getting these negative rewards. The episode's over. So you can think of this as telling you how long it takes you to reach one of these grey states. That's what we're trying to figure out. That's the length of a trajectory. One sample of this, of the Markov chain corresponding to whatever policy we choose, will tell us, you know, it'll have some, you could do some random walk around here, eventually you'll end up here, and you'll get -1 per step, and so the sum of all of those rewards tells you how long the path was that took you to a terminal state. And what we want to know is, on average, how many steps until we hit one of these 2 grey terminal states. And what we're going to do is we can consider the simplest policy we can think of, which is just uniform random. So probability of all 4 compass directions is just 1/4. And we want to know, well, how long does it take? I mean, it's not, you know, if you look at this, it's not obvious just at a glance how many steps it will take you to find one of these grey states on average. Okay, so we want to ask that question. We want to be able to solve problems like this. What's the, if you behave randomly, if you just do this random walk around here, how many steps will it take in expectation until I hit one of those grey things? Okay, and we're going to use dynamic programming to solve this. So it looks something like this. So just for now, concentrate on the left column. I'll explain the right column in a minute. Okay, in the left column, we've got our value function. So we've got a state value function, v, which is telling us the value of every single state. So this is our estimate of how many steps until we hit the grey state, until we hit a terminal state. And we're just going to start off, like I said, with the most naive estimate we could think of, which is plugging in 0 everywhere. So this is our initial estimate. So this is our V0, if you like. I think I called it V1 earlier. And now what we want to do is we want to apply one step of iterative policy evaluation. So we're going to apply the Bellman expectation equation as a backup. We're going to apply it to all states, and we end up with a new value at each of these states. So how do we do that? Well, what we do is we look at each state in turn. So if we just pick one of these states, like here, so all we're doing is we're saying, well, whichever direction we go in, we're going to get -1 reward, because we've taken a step. And then we're going to look at the value according to our old estimate, our previous estimate, which said we were going to get 0 everywhere. So we're going to basically say I'm going to get a -1 step, and then I'm going to have a reward of 0. So we're going to plug in a new value here of -1. And the same logic is going to apply everywhere except in the terminal states, where in the terminal states it's already terminal. So if we take 1 step ahead, we don't get any more negative rewards. It's like you just stay there and get 0, 0, 0, 0. So in the terminal rewards, we just have 0 at the next step, regardless. So this is like a naive 1-step look ahead to say, well, you know, whichever step I take, it's going to get -1 unless I'm already at the goal. In which case, I'm not. I know it's 0 steps until the goal. Now we have a new value function. We're going to iterate. We're going to apply the same process again. So we're going to iterate to consider some new states. So again, let's consider that same state again down here. So for this state, we're now going to do again a 1-step look ahead. So 1-step look ahead says, well, I could go north, east, south, or west. I'm going to consider each of those with probability 0.25. In each case, I'm going to have an immediate cost of -1, plus the value where I end up. So I think, at this point, I think the value of going north is -1 minus another 1 from my estimated value of where I ended up. Okay? So from this state, I think it's -2 because I'm going to average over this -2, this -2, this -2, and this -2, so I think the value of being here at this point is -2. However, if I consider, say, this state here, now I could go north, east, or south, and for each of those cases I'm going to estimate the same thing. If I go east, I'm going to see -1 minus another 1 for where I end up, so -1 for the step, and then -1 for my previous estimate of the value. If I go north, remember that I end up just sticking where I was, so it's the same thing, -1 for taking that step, and then I estimate the value of where I ended up to be -1, so -2 again. But if I go west now, I think there's going to be an immediate cost of -1, and then my estimated cost of the goal is 0. So I've got, this should be minus 1.75, I think it just doesn't fit. So I've got a 0.25 probability of just getting minus 1 reward for the immediate cost, and I've got a 0.75 probability of getting minus 2. Okay? So we iterate this process. If we keep iterating, so this is after 3 steps, this is after 10 steps, once we iterate to convergence, we see that this thing stabilizes eventually on the true value function. So this is actually the true value function to 0 decimal places. And this basically tells us, if I'm taking this random walk, how many steps is it going to take on average until I actually hit one of these grey states? And it's around 20 for some of these cases. So is that clear, this process of iterative evaluation? So now, if that's clear, we can talk about the right-hand column. So the right-hand column is basically telling us, it's just for information now, it's telling us that not only has this been useful because it's been an iterative process that kind of tells us how much reward we're going to get when we wander around randomly, and we've sort of figured that out by an iterative process that converges on the true value function. It also tells us how to make a better policy. So what we can do is we can sort of start off by looking at this, and we can ask the following question, which is, what if I was to pick actions, not randomly now, but according to the values in this grid? In other words, if I acted greedily according to the values in this grid, what decision would I make? So to begin with, I would look and I would say, well, I think everything is worth 0, so I'm indifferent to which action I take. So these arrows here, where there's multiple arrows, it kind of indicates that there's ties. We then just behave randomly according to break ties. So we start off with a random policy, but after one iteration, we're already doing something non-random, which is that, say, if we're in this state here, for example, we can see that going north, east, or south has a value of minus 1, but going west has a value of 0. So we prefer to go west here. And so we can start to see that we start to fill in more reasonable values. If we were to behave greedily with respect to this guy, we can see that we start to do a little bit better. Now, 2 steps ahead, we've got this behavior where we know to either go north or west, and so forth. And after just 3 iterations, before we've even iterated this all the way to convergence, we already have the optimal policy when we behave optimally with respect to this value function. So hold that thought. This intuition is going to be useful later, that you don't actually have to iterate this thing all the way to convergence. But the main thing I just want you to have in your head for now is that the value function helps us figure out better policies. That even though we were just evaluating one policy, we can use that to build a new policy by acting greedily. Is that clear? Yeah.
Something that is not intuitive for me is like it somehow should simulate the distance from the terminal points. But we have like this, there where we have the value function 20, we have like, for different distances, right? You see like, we have like 2 steps from the terminal point and 3 steps, the same value function, yes. This one and this one.
This one and this one?
Yes, for example.
It's just you can't see what's beyond the decimal point.
Oh, okay.
Sorry, it's just these are truncated just to fit on. So this will have a worse value than this. It's just we can't see it to precision. Yeah, question?
I don't quite understand that the policy improves, but the numbers are still computed based on taking a random. It's not fed back into the calculation.
No, that's coming next. That's coming
Okay.
next. Yeah, so for now we're just evaluating the random policy, and all I want to show you is that any value function can be used to compute a better value function. Okay, so that was iterative policy evaluation. So far, if we ignore that right-hand column, really what we've been focusing on is this problem of how to figure out the value of my current policy. And now we've got a mechanism for doing so, a first mechanism for doing so, which is to iterate our Bellman equation again and again and again, feed it back into itself, feed the value back into itself, do these one-step look-aheads, and figure out what the new value is in every state. And that's been a process that helps us figure out exactly how much reward we're going to get. Okay, so now that question was great because it leads me right into the next section, which is policy iteration. So now we're going to talk about the next problem, which is here we were just trying to evaluate a fixed policy, for example, the uniform random policy. And now we want to actually find the best possible policy in the MDP. And the way we're going to do that is by a feedback process, just as was suggested then. So let's start with this basic piece of intuition, which is we want to make our policies better. How do we make a policy better? So if someone gives you a policy pie, how can you give back some new policy that you can say for certain will be better than the one that you had before? And if we had such a process, we could just apply that again and again and again, and we would end up eventually finding the optimal policy. That's the intuition. Okay? So just first of all, an intuitive level, and then we'll do it slightly more formally in a minute. What we're going to do is break this down into 2 steps. First of all, what we're going to do is evaluate that policy. We're going to figure out a value function for that policy. So if someone gave me a policy, all I need to do is compute the value function, like we just did in the previous example in the grid world, which tells us how much reward we're going to get in expectation, like what's the average path length until I hit that grey state from any start state. So it's just filling out those numbers like we just did. And then we improve the policy. We improve it just like we did on the right-hand column by acting greedily with respect to our value function. So we just need these 2 steps. So you start with a policy, you evaluate that policy, and then you act greedily with respect to the numbers that you filled in. You act greedily with respect to your value function. And we'll define precisely what we mean by greedy, but essentially we mean precisely what we saw in the last example, where you kind of just look ahead. You look ahead in each direction, and you pick the one which is the best. So you consider each action, and you look at the value of where it takes you, and you pick the one which is best. That's what it means to act greedily.
So this policy will converge to the optimal policy, or just will converge to some policy?
It's coming. It's coming. Just be patient. Okay. So in the small grid world, we just did this once. Okay. We just started with the uniform random policy. We evaluated that policy once. That was the left-hand column, and we improved the policy once. That was the right-hand column. We looked at what would happen if we took that value function we ended up with and then acted greedily with respect to that. And in the small grid world, that was enough. So if you did that once, if you went all the way to the bottom of the left column and then acted greedily, that already gave us the optimal policy. That isn't normally the case in more interesting problems. But what is the case is that you can go round and round this process iteratively. You can basically start with a policy, you can evaluate that policy, improve it, evaluate your new policy, improve it, evaluate that policy, improve it, and eventually what we'll see is that this process always converges to the optimal policy. Okay, we'll see why in a second, but first I just want to give a bit more intuition. Yeah, questions?
When you improve the policy, then isn't it like a deterministic thing? Once you...
Yes.
Is the idea similar here?
So remember, sorry, just to explain why. So recall from the last lecture that there is always at least one deterministic optimal policy for any MDP. So it's sufficient to actually search over deterministic policies only when you're looking for the optimal policy.
So what I mean is when you do this evaluation improvement process, when you do the improvement step, your policy then is greedy on the evaluation.
Yeah.
So it's deterministic. So
Yes.
the next evaluation will be the same.
No, it'll be a different deterministic policy at the next step until you converge on an optimal deterministic policy. But you're right that after your initial policy, every other step will be deterministic.
Is that idea similar here to EM?
There is a relationship between policy iteration and expectation maximization that's a little bit subtle and has been explored in recent papers. It's not an explicit equivalence, but there's a relationship. So it's, yeah. Okay, so just in one picture, this is the idea that we're going to be using again and again, not just today, but in many subsequent classes as well. We're going to be using this idea repeatedly. So you start off with some inputs to this process. The inputs are some arbitrary value function, like this, all zeros, and some policy. And what we're going to do is we're basically going to start off by, we're going to do policy evaluation on our up arrows, and we're going to do policy improvement on our down arrows. And so what this diagram illustrates is we start off with a V and pi, and what we do is we set our value function to evaluate exactly this initial policy on this first arrow. Once we've got that policy, we act greedily with respect to that policy to give us a new policy. we act greedily with respect to that value function to give us a new policy. Once we've got that new policy, we evaluate the new policy. That gives us a value function. Once we have that new value function, we act greedily with respect to it. Once we have that new policy, we evaluate it, and so on. And what we'll see is that this is guaranteed to converge to both the optimal policy, the optimal value function, and therefore the optimal policy. So we have this cycle of evaluation and improvement. And what we're going to see over the coming lectures is how we can sort of substitute in different components here. But we'll keep to roughly this picture, but in sort of more and more sophisticated ways. But in this case, what we can say is we've seen at least one way to do policy evaluation, where we estimate V pi here. These up arrows are done using iterative policy evaluation. That was this Bellman expectation equation that was iterated to solve for, figure out the value of the policy. That was the first section of this class. And now we've seen at least one way that we can do policy improvement, which is by acting greedily with respect to our value function. And so we can just iterate this process, and we have a solution method for an MDP. Yeah, question?
So this is perfect. It doesn't matter where you start. You're always going to end up at the same.
No matter where you start, for any value function, any policy, you will always end up with the optimal value function, the optimal policy. Fundamental theorem. We'll see why shortly. Okay, let's give an example first, just to get more intuition. So we're going to have, I think it's useful just to see that some of this stuff can be applied somehow in the real world. So this is a toy example, but it's sort of indicative of something that people might care about in the real world. So it's a problem from Sutton Abato called Jack's Car Rental. And basically what's going on is there's this car rental place. It's got two different locations, and cars are rented from each of these two locations. And there's a maximum of 20 cars in each location. And what happens is there's these kind of random request and return process where the people are going to come in and randomly come in and rent cars from either one of these locations, and randomly they're going to return cars to these locations. But the rate at which they rent and return the cars is different in the two locations. And so what you get to do is every night you get to move some cars from one location to the other, and you need to do this in the optimal way so that when people actually try to rent a car, you want to make sure that cars are available to be rented. You basically don't want to end up with an empty car park when some customer comes in and tries to rent a car, because you lose money. And the question is, what's the optimal policy for shifting cars around so that you maximize your income? So it's a relatively kind of real-world scenario. We can formalize this as an MDP very simply by just considering the states to be how many cars we have in the two locations. The actions are how many cars from -5 to +5 we move from location A to location B every night. Reward, $10 per car that's rented. Transitions are the actual return and request process. And I don't want to get into the details of it. There's some Poisson distribution determining this random process in the example. But roughly speaking, the main point is that one location gets the same number of requests and returns. Like the return rate is the same as the request rate. It's a random process, but with the same rate. But the other one gets more requests than it does returns. So the second location is kind of always going to be short of cars if you don't shift things over. Not always. It's typically going to be short of cars because it gets more requests for cars than people are actually returning them. Okay? So what we're going to do is just see what policy iteration looks like. So we're going to apply this idea of policy iteration. This is all just, I know I haven't been concrete yet about the algorithm. I just want to give you a flavor of what this algorithm looks like, first of all. And so what we've got here is we're just looking at the policies to begin with. These 5 squares here represent the policies that we're considering. So the axes are the cars at the first location on the y-axis and the number of cars at the second location on the x-axis. So this is the state that we're at in our MDP. You know, whether we've got like 10 cars at location 1 and 0 cars at location 2, that would be here, for example. And the question is, what do you do in that location? And what we see from these diagrams is you kind of look here, and this would tell you, you know, if you're in that situation, you should move 4 cars from A to B. Okay, so that's what these diagrams are indicating. They're indicating the policy telling us at any stage of our algorithm what we believe the best thing to do is. And so we start off with just an arbitrary policy. In this case, we're just going to do nothing as our initial policy. And we're going to seed our policy iteration process by, first of all, evaluating that policy. And what we do is each time we evaluate a policy, we build up a value function, which looks something like this. Okay, we build up a value function saying, if I take the actions that are recommended, in this case do nothing, I'll end up with some surface that tells me how much money I'm going to make doing nothing. And then what we do is we act greedily with respect to that surface. We basically pick the action which, according to my current value function, looks best. So I do like a one-step look ahead, take the action which looks best according to my current value function, and that gives me a new policy. And we see that immediately after one iteration we gain some information. We see that, on the whole, we think that we should be shifting cars over around 5 from location A to B quite often, and sometimes we should be shifting cars back again, -1, -2, -3, -4, but most of the time we should be shifting to the location with less cars. We've already figured that out, the one that gets less cars returned.
But we have assigned probabilities how many cars are rented and returned, right?
I didn't understand the question, sorry.
So, like, to estimate the next step, we need to know how many cars, let's say, were rented and how many cars were returned.
We don't need to know exactly how many. So the question is, do we need to know how many cars were rented or returned?
Oh, just probability on this.
So we need to know the probabilities. Yeah.
Yeah.
So we need. So we're doing. So remember, we're just doing planning. We're just doing planning. So the dynamics of the system are known. In this case, the dynamics of the system are the return rates and the request
Poisson
rates
distribution, right?
given by Poisson distribution. So we know those. We can use those. That's our PSS prime. So we know the probability that we're going to have a customer come in and request a car, and we know the probability that they're going to come and return a car to each of the locations. So those things are known, and given that information, we're trying to figure out what's the best behavior strategy, like what should I be doing, shifting. So it's like, typically in industry, how people use this is someone comes up with a model of their system. That model might not be correct, but then they use dynamic programming to solve for their model. So you can think of this as like some simplified model of the car rental. The Poisson process might not be accurate, but there's some way in which the dynamics are described. Okay. And then what we do is we take our new policy. So this was just like in the small grid world, we just did one step, and then in the small grid world, that was already optimal. This is a more interesting problem. This is not the optimal policy. So what we do is we evaluate this policy now. We come up with a new surface, a new value function that looks something like this, and we act greedily with respect to that new value function. So now again, we do a one-step look ahead. We say, given that we think customers are coming in at a particular rate, we do this look ahead. We figure out which action is going to be the best. We evaluate, how much money we think we're going to make by using this value function and doing a one-step look ahead on our current estimate, and that gives us a new policy. Then we evaluate this policy, we come up with a new surface, new policy, new surface, new policy, and after 1, 2, 3, so I guess these 5 policies, on our 5th policy, or the 4th iteration of the algorithm, we already have the optimal policy. This is converged now. I think there's still a small change from here to here, but after this it doesn't change anymore. The problem stabilizes, it finds the optimal solution. And so I've already had quite a few questions where people ask, well, why is this actually stabilizing? Why does this work? So I'll talk about that in the next 2 slides. Before we do that, are people clear on the intuitive way this algorithm's working? Like what's going on? This is a great time to ask questions. Don't just kind of feel, what's going on? I don't understand.
How can I read the policy off that grid?
Okay, how can you read the policy off the grid? So you read off the state. So the state is given by any point here. So if we consider a point here where we say got 17 cars at this location and 10 cars at this location, we're just looking at this number here, and it's 1. So that's telling us that we should move 1 car from location A to location B. So these are it's like a contour map. So this is a contour map of the policy. Sorry if that wasn't clear. So we're reading off for each region what the policy is within that contour map.
What's on the vertical axis there, 6, 12, and 420?
Okay, good question. So what's on the vertical axis? So this is the surface telling you the dollars return that you're going to get. Like how much money are you going to actually make? Like this is the question these guys want to know. It's like, ultimately dollar value, how much money am I going to make following this policy? And what this tells you is if you're in any situation, so if you're in a situation where you've got no cars in either location, you're still going to get money because eventually over time you will start getting cars coming into these locations. But it's less money than if you've got 20 cars at each location. So you should expect some kind of slope upwards. And what this is telling you is the total dollar lifetime revenue that you're going to get under some discount factor, which was probably on the last slide, telling you how much you prefer to get dollars now than dollars tomorrow or the next day or the next day. So this is your income. This is the thing we care about. So this is really intuitively, we're building our policy by looking at the right thing. We're looking at how much dollar income am I going to get by following one of these policies, and then choose the actions that maximize dollar income and the total amount of lifetime value you're going to get by following this whole policy.
But there's no cost in moving a car from.
There's no cost in moving a car in this example.
Okay.
Yeah.
Sensitive is the convergence rate to your pi zero.
The question was how sensitive is the convergence rate to pi zero? And we'll see later, at least for some of the algorithms, the convergence rate is independent of pi zero. But in practice, that doesn't answer the question, which is that you might just, your pi zero, your initial value may be way off, and your first policy may be way off. And so clearly, if you start with the optimal policy, you'll get to the optimal policy faster. So it does matter, but the convergence rate is independent of the initial value and policy. Okay, so let's just do this a little bit more formally so that people understand, get more comfort with this idea that this really does work. Okay, so let's say what it means a bit more precisely to do a policy improvement. So we're going to start off with some deterministic policy for now. So as someone pointed out in the audience, after one step of acting greedily, we're stuck with deterministic policies anyway. So we may as well just consider, when we want to do our step of this algorithm and understand convergence, let's just imagine we started with a deterministic policy. Because after just one iteration, we're going to have a deterministic policy anyway. Acting greedily always makes you deterministic. And so how do we come up with our new policy? And the way we come up with a new policy is by acting greedily. Well, now let's define what that means to act greedily. So acting greedily means that we look at the value of being in a state and taking a particular action, and then following your policy after that. That's the action value. That's precisely the action value. So what we want to do is pick actions in a way that gives us the maximum action value. So we want to pick the action that gives us the most Q. So that's what this argmax means. It just returns the action that maximizes this quantity. And Q, remember, is just the immediate reward plus the value of the next. So the immediate reward when you take action A plus the value function, the state value that you get where you end up. So that's what it means to act greedily. So now let's understand. So the first thing to understand then is to show that if we act greedily, that the greedy policy at least improves the value that we're going to get over one step, over this immediate one step. Let's not worry yet about what happens after that. Let's just consider one step and see whether we get more value over one step. And the answer is yes, and the reason is, okay, so if we start off with our action value here, so what we're trying to say, what we want to show is that if we were to follow, so what this means is we're trying to say, if we were to take our new policy, pi prime, so pi prime is our new policy, our greedy policy, if we're going to follow our new greedy policy for one step, and then follow pi afterwards, forever afterwards, we want to know whether that gets more or less value than just following our policy all the way from that state. Okay, so that's the definition of v pi. This tells us how much reward we get if we just follow pi all the way from S, and this tells us how much value we'd get if we started in S, followed action A for one step, and then followed pi after that. That's the definition of Q. You take action A for one step, and then you evaluate the policy after that point. Okay, so this thing, we can just plug in the definition of the argmax to say, well, if we are actually selecting actions by taking an argmax over the Q values, that means that we're going to basically be always taking the action that maximizes our Q pi. So that gives us this term here. So we're always picking the action we're picking is always the one that gives us the most Q pi. And so we can just say that the value of the thing which gives us the most Q pi is the max over our Q pi's. And the max over the Q pi's has to be at least greater than or equal to one particular Q pi. So the max over all actions has to be at least as good as one particular action that we could plug in, which is the one we were choosing before. And the one we were choosing before, so this is now basically saying the value, if we take policy pi for one step, and then follow policy pi forever after, so that's following policy, that's the same as following policy pi all along. You take pi for one step and then pi forever after, and that's the same as the thing that we started with, v pi. So all of this, that's a long-winded way to say that the value function improves over one step at least. That if we just take our pi prime for one step, we're going to get at least as much reward as the policy we started with. Okay? And then all we have to do is iterate this using a telescoping argument to show that now we know, so we've basically got our result, which tells us that v pi is less than or equal to this q pi term. Okay, that's our premise. And so what we're going to do is we're going to say v pi is less than or equal to q pi with this. So taking our greedy policy for one step is better than the thing we started with. That's what this tells us. If we follow our greedy policy for one step, it's better than what we started with. And all we're going to do is we're going to unroll this inequality multiple times to show us, first of all, that it's better for one step, then that it's better for two steps, then that it's better for three steps, and then that eventually that it's better for the whole trajectory. Okay? So specifically, we take our q, we unpick q in terms of the Bellman equation by saying that the definition of q is the reward plus the discounted value at the next state. And then what we do is we apply our same inequality to this v prime at the next state. And we unroll this. So we use the same inequality, we plug it into v pi at the next state, and that tells us the next that we're going to get at least as much value for one step, and then for two steps, and then so forth. So what have we got so far? If we come back to this, just one second. So all we've showed so far is that if we pick this greedy policy, that the value of the greedy policy, the total amount of reward we get by acting greedily, is at least as much as the policy that we had before we greedified it. So we don't make things worse, ever. We always make things, at least make them better. We haven't yet said that this is guaranteed to keep getting better or to reach the optimal value or anything like that. Okay? Right. So now we want to know, well, you know, what happens? Is this process actually going to take us to the optimal value? If we just keep improving and improving and improving. So let's consider what happens if this process ever stops. So if we ever have equality. So we've got two cases. Either we just keep getting better and better and better, or at some point this is going to stop. And what we want to know is that when it stops, that we've actually achieved optimality. So we're just going to plug in. It's the same equation we had before, but now we're going to plug in equality instead of this less than or equals. And we want to know, well, what do we know about this? And the good news is that if improvement stopped, then we've just written out the Bellman equation. In other words, if this thing is satisfied, then we have satisfied the Bellman optimality equation. So we've basically got v pi here, and we've got the max q pi here. So we've basically said this is equal to this, and that's actually one form of the Bellman optimality equation, that the value of state S is equal to the maximum over the value over the q values. That's the one-step look-ahead form of the Bellman equation that we saw in the last lecture. I know some of this you might need to look at afterwards, but I'm just trying to give you some flavor of how this argument works. And so if the Bellman optimality equation is satisfied for this particular v pi, that tells us that pi must be the optimal policy. So if we've satisfied the Bellman optimality equation, that's the definition of an optimal policy. That anything which satisfies the Bellman optimality equation is optimal. Okay, and we'll see some argument for that at the end of the class as well. Okay, so the way to think of this is basically what we've shown is that we've defined what it means to act greedily, which is you start with your value function, you use that value function to do a look ahead, and you pick your policy that's now better. And what we do is we see that gets better and better and better and better and better. We apply that process again and again and again. And if that process of improvement ever stops, the only time it can ever stop is if it's actually satisfied the Bellman optimality equation, in which case we're done because we found an optimal policy. Okay? So, we have a solution method. We've seen policy iteration solves MDPs. So we started off, so summary so far, we started off with a way to evaluate a policy. Then we found a way to improve a policy. We put these together into an iterative algorithm, and we've shown that iteration actually does solve the MDP. It finds the thing that we want, the optimal, the best possible thing you can have in that whole MDP. We could solve problems like the Jack's car rental and so forth using this approach.
Is there
some kind of intuition to explain why you can't stop at a local maximum?
Yes. I'm going to try and give that at the end, if it's okay. It's a more... there's a contraction mapping argument, which I think is the easiest way to understand it. It's a little bit formal, but... so, essentially, in one word, basically what happens is when you apply the Bellman equation, to your value function, you bring your value function closer and closer together in value space. And yeah, I think I'll need to do it properly or not at all. Sorry. Yes.
How does this relate then? For instance, I mean, you suggest we just go greedy on every step, right, to improve. But for instance, in one of your game examples, where there was a shooting game, you didn't, when there was this mothership, you didn't go for like immediate reward in the next step. You went for the mothership, which was sort of delaying and more targets coming in. You know, I mean, it was not like.
So the question is, so let's not confuse what's going on at each iteration with what we end up with. So each iteration we're acting greedily, but being greedy doesn't mean that we only look at one step of immediate reward. Being greedy means that we look at the best action we can take if we optimize over all actions we can do for one step, and then look at our value function, which summarizes the whole future, all future rewards we're going to get going into the future, but under our previous policy. Okay? So if your previous policy was already shooting the mothership, you would see that. You would see that I'm going to consider all the things I could do in one step, and amongst those things that I can do, some of them are going to kill the mothership, and some of them aren't. Coming back to the previous question, I think one piece of intuition I can give is that as you can think of policy improvement as a partial ordering over policies. So basically what we've defined is something which says when one policy is better than another. So one policy, you can say that one policy is better than another if it gets more, like if the value function is strictly better than the other policy. Like if the value function has higher values than the other policy in all states. That gives you a partial ordering over policies. And so you basically, because you've got a partial ordering, you can only climb up so that you've got a lattice of possible values where you're just getting better and better and better in value. And the only time you can ever reach the top of this ordering is when you reach the optimal value function. It's not possible to have something which is kind of worse than some other policy in some states and better than policy in the other states, because we're defining an ordering over policies that just looks at the whole value function, that looks at how much better they're getting. And so you can only get better and better and better and climb in value until you reach the pinnacle of this sort of lattice of possible policies.
So it's a least fits point argument, is it, to prove that? Is this contraction mapping thing, is that related to some sort of metric space? And
Yeah.
Okay,
Okay. Right. So let's just change gear a little bit and talk about some... Oh, sorry, question. Is it necessary for the value to be the true value under the policy?
Yeah, to do policy evaluation until convergence.
This slide. Great, thank you. I think this is the slide. If at the end of this slide it doesn't answer your question, then ask me again. Okay? Okay. So, so there was a great question there, which is essentially, we saw in this, if we go back to our example of the small grid world, we saw that even after doing a very approximate job of figuring out the value of our policy, so even if you didn't figure out exactly your VPi, even if you just kind of did a few iterations of your Bellman expectation equation, you got some very crude estimate of how good each state is, and act greedily with respect to that, that was already enough in this problem. That was already enough to come up with a much better policy. We didn't need to evaluate this thing perfectly and then act greedily with respect to it. In fact, all this additional work gained us nothing. Like all these different iterations, they gained us zero information when we actually took our greedy step. We ended up with the same policy. So in some sense, you could think of iterations 4 to infinity of our inner loop as being wasted work. And so the question is, do we have to take those steps, or can we truncate our evaluation process and use an approximate policy evaluation in our inner loop rather than an exact policy evaluation. Was that the question? Good. And so this approach is called modified. It's a very uninformative name, but it's called modified policy iteration. And the basic idea is to stop early. So there's two ways you can think of this. One thing you can do is just to have a stopping condition where you get close enough to the value function you care about. So you could say, look at your Bellman error, look at how much your Bellman updates are changing the value function. When they are only changing the value function by some tiny amount, epsilon, then you can just stop. So you don't need to go all the way to get every decimal place perfectly right. You can choose when to stop and you can apply your policy improvement. But even that would be probably wasting effort. So what happens if we just do something more naive, like take k iterations of iterative policy evaluation, like 3 in the small grid world, and just do 3 steps of evaluating the policy, improve your and then improve. 3 steps of improving your policy and then improve. This is a perfectly reasonable algorithm, and it still converges to the optimal policy. I'm not going to prove that, except in one special case, which is the extreme case of this, which is when we actually just stop after k equals 1. In other words, we just do 1 in a loop of basically we look at the Bellman equation once, we update our value function, we act greedily with respect to that value function, and then we immediately proceed. So it's the extreme case of that. And this extreme case is actually equivalent to value iteration, and we're going to have a whole section on that. It's probably the most popular method for dynamic programming. Okay. Right. So I would just, before we go into the details of value iteration, I want to return to the basic principle of dynamic programming, which was the principle of optimality. So if you remember, we can subdivide a policy, any optimal policy, we can subdivide into 2 pieces. So I have to take an optimal first action. So if my first action is optimal, and then after that I follow an optimal policy from wherever I end up, then we can say that the overall behavior is optimal. Okay? So we can break down our description of what it means to have an optimal policy in terms of finding the optimal policy from all the states that you could end up in. Once you do that, you then just need to do this 1-step look ahead, figure out what the best first action you could have taken is, and you're done. So this is the principle of optimality applied to policies. You don't need to consider the whole problem at once, you can break it down into these sub-pieces. So this gives us a theorem, the principle of optimality for policies, and the way to think of this is just a formalization of exactly that intuition, which just says that a policy achieves the optimal value from any state S. So it achieves the optimal value. In other words, the value of that policy is the optimal value function from state S. So this policy really does maximize the maximum, gets the maximum juice out of our MDP, this policy, if and only if, for any state that we can reach, the policy that we follow is optimal from that state onwards. So a policy is optimal if for each state that the wind might blow us to, that policy would behave optimally from that state onwards. Okay? So that's a requirement for optimality. So we're going to use this to build a value iteration algorithm. And so the basic intuition is, like, you can think of this as like a backward induction algorithm, that we sort of think of the value function as caching our solutions to all of our subproblems. So the wind's going to blow us to some state S prime. And now we're just going to assume that we have the correct solution to that. So we're going to assume that someone has told us the optimal value from S prime. Someone's told us how much juice we can extract from the MDP from that state onwards. And now the question is, how do we use that information to build an optimal value function at the previous step? And all we need to do now is a 1-step look ahead. So we're building our 1-step look ahead tree, this time using the Bellman optimality equation. So we're building a 1-step look ahead tree to say that all we need to do is to do like this 1-step look ahead, look at the leaves of our tree and back them up. So we start off with our inductive premise that we know the optimal solution from the leaves. We back this up by doing a 1-step look ahead up the tree. We maximize over all the things we might do, and that's going to give us the optimal thing to do at the root. And the idea of value iteration is just to apply this update again and again and again. So instead of someone telling us the optimal solution from S prime, we're going to find this iteratively by starting with an arbitrary value, backing this up to give us a new value function, plugging in that new value function, backing that up to give us a better value function, and so on. And we're going to just iterate this process. And again, we're going to see that this converges on the optimal value function. So the intuition, I think, that helps understand how this works is that you sort of start off at the end of your problem. Imagine that you start off at the end of your problem and someone tells you what the final reward is. Someone tells you, if you're one step away from the goal, then you're only going to get -1 for one step, for example. And then you work backwards, figuring out more and more of the optimal path until you figured out the optimal path all the way back. Now, we're not actually going to do it by finding the goal and then working backwards. We're going to do it by just looping over our entire state space. And this is better because it still works if you've got loops in your MDPs or if you've got stochastic MDPs. And we just want a general procedure that kind of, but the intuition is still there, that we work backwards through the MDP. Yeah, question?
This theorem you have mentioned on the slide, it only works for the states we can actually reach. But on this slide, it seems that you are looking at all the possible states without sort of looking.
Well, we're looking at all the possible states, but reachable, like if something's unreachable, it just means it has 0 probability.
Right.
So it just doesn't enter into this equation. So it's not a requirement that you get the V star correct for those states because they don't affect this equation.
So it's taken care of.
Yeah. Okay, so let's do a simple example. So this is another small grid weld. It's a very simple grid weld, this one. There's just one goal state here. So same idea as before, you can go north, east, south, and west. And we're just going to look at, we're trying to figure out, well, what's the optimal path length? We're basically trying to say, how many steps does it take to reach this goal? But whereas before we were looking at some random policy, and we were just trying to evaluate that random policy, we were just doing some random walk, and we wanted to know how long until you hit the grey state. Here we're trying to find the shortest path, the best path. We want to know what's the optimal policy for reaching this G. If it's -1 per step, what's the shortest path from any position on this grid to that grey state? And intuitively, the way to solve such problems is that you can kind of start off with some initial state that tells you that it's 0 at this state here, and then you kind of work your way backwards. So once you know it's 0 here, you know that from each of the states adjacent to that, the cost is -1 to reach that. It takes you 1 step to get there, 1 step to get there. Once you know it's -1 here, we know that it's -2 from this state, -2 from this state, -2 from here, -2 from here, and so forth. And so the values propagate through in successive iterations until eventually we figure out that it's, that once we've seen that it was -5 from here and -5 from here, we can do a 1-step look ahead and see that the optimal solution is -6 from this corner state here. So the point I was making in the last slide is that if we were to just order our computation, given perfect knowledge of how this structure would work, we wouldn't have to update every state. We would just start in the corner and kind of sweep over backwards, and this starting at the goal and kind of working our way back to the state we care about. But in general, if we do synchronous dynamic programming, we don't know in advance where the goal is. We don't know in advance that there even is a goal. There might just be loops and rewards, and things might go on forever. And so what we do is we update every single state. So we start off with some arbitrary estimate of all these zeros, and we update all the states, not just the ones next to the goal. We update this state as well. We don't know until we try it, until we do our 1-step look ahead. We don't know. It might have been, if we did a 1-step look ahead from here, this might have taken us to the goal. And so we update everything. We update all states by doing a 1-step look ahead, by saying, okay, if I look ahead here, if I maximize over all of the things which I might do, so from here I can do a 1-step look ahead. I can choose to get -1. So I can choose, every step I take will get me -1 reward, remember? So I can choose to get -1 reward and end up in a state that has a value of -1, or a -1 reward end up in a state that has -1, or the same here or the same here. So no matter what I choose, I'm going to get -2 from here, which is what we fill in here. But if we start with this state here, I can choose between these states, which will have a reward of -1, and then I'll end up in a state with -1, giving me -2. I can also choose to go up here, which has a value of -1 plus 0. And so in this case, we maximize over those choices. We get to pick the best one. And so now we fill in a new value of -1 here. Okay? And we do that for all states at every iteration, and we update our we get a whole new value function. So we started off with all zeros. We get a whole new value function. We plug that back in. We get a whole new value function, until eventually we end up with the optimal value function, the thing which really tells us the shortest path in this case. Is that clear? Yeah, question.
The -6. How would we get -6 from that position?
1, 2, 3, 4, 5, 6.
But you don't get -1 when you
Sorry, the
the
other way.
final step.
1, 2, 3, 4, 5, 6. So the definition of the small grid world was that every transition gets you -1 reward as you exit the state. So exiting here gets you -1, exiting here gets you -1, -1, -1, -1, and -1. So there's 6.
-5, isn't it?
Like summing those things. At every step you get an additional -1 per step. So we count 1, 2, 3, 4, 5, and 6 transitions.
Oh, so you count the last one as well.
Yeah. So the reward was -1 upon exiting the state, just like we had in the previous class. Yeah, question.
I was wondering, so we're working backwards from a final state. If there is no final state, can we also apply dynamic programming then?
Yeah, so let me be absolutely clear about this point. The final state and working backwards argument is just to give you the intuition of what the algorithm is doing under the hood. In practice, the algorithm doesn't even know that a final state exists. If there is no final state, the algorithm will still work. If the algorithm goes on forever, if you're in an MDP that's ergodic and just goes on forever, a continuing MDP that has some discount factor and just goes on forever, dynamic programming still works. It will still find the optimal solution. This shortest path example is rather artificial. It's just to give you the intuition of how information propagates through the system, such that you find the correct answers at the end. There doesn't need to be a goal state. You can have multiple goal states, no goal state at all. So, is that clear?
Yeah.
Good. Yeah, question.
If I know the MDP, and if there is a level state, I do know that I could really propagate backwards and just compute for the states near the goal and so on.
Okay, so you've preempted the next algorithm again, but I'll come there in just a second if you don't mind. A couple of slides from now. Okay, so let's finish with value iteration. So let's try and understand this then. So value iteration. So we've seen sort of the intuition, we've seen a figure about what's really going on. So we're trying to find the optimal policy. We're trying to find the optimal policy as some MDP. So again, we're trying to do planning. So I just really want to emphasize again, we're not solving the full reinforcement learning problem here. Someone's telling us the dynamics of the system. Someone tells us the probabilities that you'll end up in all the next states, and someone tells us the immediate rewards you'll get. So someone's giving you the environment, telling you how that environment works, giving you the source code that tells you exactly what's going to happen next. Okay. But what we want to do now is we want to solve, given that someone has given us this MDP, we want to solve it. We want to find the optimal value function. So in the previous section we had policy iteration. Value iteration is another mechanism for solving the MDP. In the first part of the class today, we saw how you could use the Bellman expectation equation as a backup. You just iterated the Bellman expectation equation again and again and again. That found you the value function for a given policy. And the idea of value iteration is to take the Bellman optimality equation and iterate it again and again and again. And that gives you the optimal value function. So it finds the best value amongst all policies. So we start off with our initial value. Again, this can be arbitrary. The convergence rate is independent of where you start, but of course in practice it can matter. And we just iterate over whole sweeps of our state space. We look at every single state in our state space. We update our value function everywhere in that state space. So that's what it means to do synchronous backup. So each iteration, we consider each state in turn, and we do one of these kind of one-step look-aheads from that state, using our previous iteration to seed the values. We build a whole new value function, and then we build a whole new value function again, and we build a whole new value function again. And the question correctly earlier was, do you always have to build the entire value function? And we'll see that you don't actually in the next slides. But, convergence to V star, we can again prove using a contraction mapping. So let's think about the difference between value iteration and policy iteration. So So one thing which is apparent is that we're not building an explicit policy at every step. We're just working directly in value space now. We're not, before we had this alternation between values and policies. We kind of used our value function to build a policy, used our policy to build the next value function. Value iteration goes directly from value function to value function to value function to value function. And you might ask the question, well, what does it mean? Like if you just stop this algorithm here and look at the value function, does that correspond to any meaningful value function? And the answer is no, not necessarily. It might not be the value for any real policy. It might not be achievable by any actual policy. But at the end of this process, we know that we really have the value function for the optimal policy. And so this is exactly equivalent to doing modified policy iteration with k equals 1. And the reason is that we're basically, if you were to try and evaluate your policy for just one step, then you're taking the greedy policy, which is an argmax, and you're evaluating an argmax policy, and that's giving you a max. Okay, so if you do an argmax and evaluate it, you kind of get the max out just over one step. So you actually recover the Bellman optimality equation.
What do you mean that this value iteration doesn't, for example, doesn't correspond to any, could not correspond to any particular policy?
So I mean that the intermediate v's that you get may not equal v pi for any pi. They're just intermediate constructs that we've created by iterating some algorithm, and at any given moment they might not be the value function of any real policy. It's not like policy iteration. Policy iteration, every step we constructed a value function that was the value function for a particular policy. Value iteration doesn't do that. It's more like modified policy iteration. It's more like, if we just go back to the small grid world again, sorry I keep going backwards and forwards through these slides, but it's more like, if we go back to this algorithm, it's more like you just do one step of evaluation and then immediately act greedily with respect to it. This value function, what's the semantics of this value function? Well, it was just an intermediate step along the way of figuring out what the real value function was. But it's just some numbers, really. But we're acting greedily with respect to that and moving on already, straight away. And what value iteration does is it kind of combines the step of generating this greedy thing and evaluating it into a single step of computing the max. So it doesn't build the policy as an intermediate step. Yeah.
So if I look at the values, some intermediate values for these value functions, and I look at the policy that they imply, if I really computed the value under that policy, it could be different from the one by
I'm not sure I follow. So you can look at the intermediate value at any iteration of the algorithm.
yeah, if I just look at one intermediate value.
Yes.
And consider the policy given by that value, so in which states choose the
If you make a greedy policy
yes.
with respect
and
to that.
really evaluate the value under that policy,
Yes.
then I might get something different from the value I started with.
Yes, you would get something different. You would get something. In fact,
You
you'd get
get
something.
something
You'd get something
different.
better from the policy improvement theorem that we saw earlier. You would end up with something which is your value function would go up.
Yeah, so in fact I get the new stuff.
Well, yeah. So
Yeah,
it's like you would be mixing value iteration with policy iteration if you did that. It's like you would stop doing your value iteration and then you start doing policy iteration, where you basically take the value function you took and you start to build policies in the way that we did in policy iteration. So you can mix the algorithms. That you could do that in principle, and that would also converge.
Just one more question, because before when we proved that our value function always become bigger, but from the example with this grid we see only it become smaller and smaller, right? We add minuses. So
Okay, so it's a great question. So the question was, here we see the values getting smaller and smaller. The theorem showed us that the value of a policy is getting bigger and bigger and bigger. So first of all, that was the policy iteration, not for value iteration. So that was, I think this again illustrates the difference between building these intermediate values and actually evaluating a true policy. Okay, so if you were to actually evaluate any policy along the way, if you were to fully figure out the value of any different policy,
But you can
and then look at the value function of one policy, and build out this thing, and then the value function of the thing which acted greedily with respect to your values, the value function would be getting better. You'd be getting more reward from that thing than the other thing. We never said that the iterations of value iteration were strictly going up in value. That wasn't what we said. It's a different value iteration and policy iteration are doing different things. This, again, it's because we're not constructing real value functions for real
Right,
policies
on
here.
the previous example, like when we used only like policy iteration, it was the same case, but then we would change the policy, and for the next policy we would show that the value function increased, right? That was very the case.
Yes. Okay. So right, let's just get back to where we are. Okay. So one last slide on value iteration before we move on to some extensions. So this is just the same slide we saw earlier for the Bellman expectation equation, just to show that the same logic applies for value iteration as we saw for this iterative policy evaluation earlier. In other words, we're doing synchronous sweeps. So in every iteration, each state gets a turn to be the root of this diagram. What we do is we start off, we fill in our previous iteration. So we start off with our old value function vk. So iteration k of the algorithm, or iteration k plus 1. We put in our old value function at the leaves. This is whatever we thought the value was at the leaves for 4. And now, each state gets a turn to be the root of this diagram. We do a one-step look ahead from each state in turn. And for that state, what we do is we look ahead and we maximize over all the things that we might do. And we take an expectation over all the things the environment might do. And we compute by that one-step look ahead, taking an expectation here and a max here. This arc means a max in these diagrams. And we take this, we back this up all the way through here, doing this one-step look ahead, to give us one new value in our new iteration vk plus 1. And then we do that for all states. Every state gets a turn to be the root. And we figure out our new value function vk plus 1. And then we iterate. We plug in our vk plus 1 at the leaves. And we figure out now our next iteration. We plug those things back in at the leaves. We pass it all the way back up again. And so what we're doing here is we're taking our Bellman optimality equation and we're turning it into an iterative update. So if we didn't have our iteration things here, if this was just v being equal to v, this would be the Bellman optimality equation. This is the Bellman optimality equation, except that what we've done is we've turned it, instead of being an equality, we've turned it into an iterative update. And so value iteration, you can just think of, you take the Bellman equation and you try and get closer and closer to satisfying this thing by just feeding it back into itself again and again and again, until eventually what we'll see is that, when you keep feeding these the values that you compute back in at the leaves, eventually this thing must settle to the optimal value, and you've solved the problem.
Should there be a bracket at the bottom as well, or no?
Where?
The second line?
Here?
Around the max? The second line, sorry? Yeah.
Ah, I see. Yeah, this is a max over the whole thing.
Over the whole thing, okay.
Yep. Yes, thank you. Okay. I don't think we'll have time to do this, but I really encourage you to have a look at this little demo. If you just write this down, or it's on my slides for afterwards. It's just a demo that kind of lets you click and mess around with value iteration and just see. It's basically a larger grid world, where you just get some sense of how value iteration propagates values through a system. So it's just the same as this, but you kind of see it on a much bigger grid world and really get some intuitions and get to play with how quickly it updates and so forth. I think it's quite a fun little example. Okay, so far we've talked about synchronous dynamic programming. We've talked about ways to do these complete sweeps, update everything. And I just wanted to summarize this. So this slide kind of summarizes what's going on. So before we go on to extensions, this is really, if you get this slide, you're doing well. This is the main intuition, the point I'm trying to get across. Okay. So there are different problems that we're trying to solve. All of these are planning problems. In all cases, the MDP is given, and we're just trying to solve for that MDP. But there's two types of planning problem: prediction and control. In the first case, we're trying to solve to say how much reward you get from some given policy. To figure that out, we use the Bellman expectation equation, and so the Bellman expectation equation defines, that's the Bellman equation that defines what it means to have a value function when you're doing prediction. And if we take that Bellman equation and turn it into an iterative update, then we end up with the iterative policy evaluation, which was the first part of today's class. Okay, so you take the Bellman equation, you iterate it, it gives you V pi. It gives you the thing which tells you how much juice you're going to get from your current policy, from some given policy. Then we considered control. We considered two different ways to do control. First of all, using policy iteration, and secondly, using value iteration. These are two different families of algorithms that both address the same problem type, which is how to get the most possible juice out of your MDP, how to maximize the total reward, how to find V star now rather than V pi, and hence the optimal policy. The first approach was to again use the Bellman expectation equation and iterate over the Bellman expectation equation to evaluate your policy, but then to alternate that process of evaluation with a process of policy improvement. So that was the idea of policy iteration, that we first use the Bellman equation, the Bellman expectation equation, to solve for our V pi, and then we act greedily with respect to V pi to give us a new pi. And we alternated that process, and that gave us the policy iteration algorithm. And then finally, we moved on to value iteration algorithm, again addressing control. The Bellman equation we look at now is the Bellman optimality equation with the max in the equation, the thing which really tells us how V star relates to itself, how the maximum reward you can get out of this MDP recursively relates to itself. And the algorithm, when we then turned this thing into an iterative update, we ended up with value iteration. Okay, and what we saw as well is that between here and here, between these two lines is a spectrum, and that spectrum is the modified policy iteration algorithm, where if you go all the way down to k equals 1 to just only evaluating this thing very crudely, then you can recover the value iteration algorithm. Okay, is that clear? I really want to make sure people get this slide. Okay, so all of these algorithms so far have been based on state value functions. So the complexity of doing this with state value functions, if you have m actions and n states, what's the complexity? How much does it cost to do value iteration? Well, for each iteration, is basically we're considering n states, and for each state we're considering n possible successor states, so that gives us n squared complexity, and then there's m actions, so every iteration is order mn squared in cost for synchronous value iteration when you do a complete sweep. That's not great for big problems, but it's better than the alternative. So you might wonder, well, why haven't we been using the action value function, which we will in subsequent lectures. So in subsequent lectures we'll apply these same ideas with the action value function, and there's very good reasons to do so that we'll see later. But for now we haven't been, and the reason is that there are Bellman equations for Q that we saw in the last lecture. You can turn those Bellman equations for Q into iterative updates, and you can update Q, or you can update Q pi or Q star to do prediction or control respectively in just the same way. So there's value iteration, policy iteration, and iterative policy evaluation methods for Q, which are equivalent to V. So one reason we haven't discussed them is that they're high complexity, that you have to now, you start with your Q, so you have to consider all state action pairs, so that's mn, things that you consider, and now we're considering all next state actions that we take at the successive step, which is another mn, so you get m squared n squared, so it's just a more expensive version of value iteration. But there's very good reasons to do this later, which we'll come back to, when we want to do model-free control, when we want to do the full reinforcement learning problem. Q lets us get away from having to do a one-step look ahead. It helps us avoid knowing the dynamics, because you can pick actions just by looking at Q. You don't need to look at the dynamics for one step and then pick the best thing. Right. Okay. We have another 7 minutes to cover some extensions. So let's do that. So this is just to try and outline some of the ways in which you can take this machinery. These are really common. It's not like these are esoteric things. These are some of the things that people do in practice, to make dynamic programming more practical. So there is a good set of things to know about. So first of all, there was the question earlier, which is, what happens? Do you have to look at every single state and update every single state in each sweep of your algorithm? And the answer, of course, is no. Often that's wasting a lot of computation. So we're now going to talk about what's called asynchronous dynamic programming, which basically, now you just pick any state you want to be the root of your backup, you back up for that state, and then you can move on immediately. You can plug in your new value function back in at the bottom without having to wait until you've updated every single state. So iterations, we're going to break this relationship between iterations updating every single state in our state space, and we're going to come up with more efficient algorithms as a result. So the main idea is to reduce computation. That's why we're doing this. And a nice result tells us that basically, as long as you continue to select all states, doesn't matter which order you select them in, as long as you continue to select everything at least sometimes, then your algorithm will still converge to the optimal value function. So this all still works. Value iteration, for example, still works. Policy iteration as well. Okay, so we're going to consider 3 ideas very briefly: in-place dynamic programming, prioritized sweeping, and real-time dynamic programming, all of which are asynchronous methods. So they basically are different ways to pick which states that we're going to update. Okay, so we're just not going to do complete sweeps. We're not going to naively update every single state in our state space and incur that big cost we just saw in the last slides. Okay, first idea, in-place dynamic programming. So this is more like a programming trick, if you like. So if you were sitting down to implement dynamic programming, you would probably think of this idea straight away, because it's an easier way to program the same algorithm. So if you're actually trying to do synchronous evaluation the way we described it, you kind of have to store, at any given time, you have to store 2 value functions. You have to store your old value function, which is what you plug in at the leaves, and you also have to store your new value function, which is the thing you're computing at the root. And so that's these things in red, that you're always updating your new value function, your next iteration, by plugging in your old value function at the leaves and doing this one-step look ahead to figure out how much value you're going to get by looking ahead. So we kind of, what we do is we do a sweep over this, we update every state in our new state space, and then typically you just switch these things over. So your old, you switch your new values into your old values, and then you repeat. So that's how you would actually program this. And the idea of in-place value iteration is just to forget about this step, just forget about differentiating old and new. You basically just say, we're going to sweep over it, and in whatever order we visit states, we're just going to use the latest version. We're going to immediately update our value function, and now for whichever states we happen to have visited, we're going to use the latest value. We're not going to plug in the old value, we're going to plug in the new value here. We're going to plug in the latest information that we've got at any given time. So if I visited a state before, and now I see that state as a leaf, I'm going to use the new value that I've already computed. And because this has more new information in, it tends to be more efficient. And the only question now is, how do you order states so as to compute things in the most efficient way? And it turns out, in some states, in some problems, you can be much, much more efficient. So imagine you've just got like a single corridor, and you happen to sweep over your states in a kind of goal towards source direction. Well, then it turns out that in-place value iteration in one sweep through all of your states will have already computed the optimal solution. You don't need n different sweeps, because you start at the goal, you figure out the optimal value of the goal, you step back one, and now you already plug in your latest value there. You use that, step back one state, use your latest value figured out, so you're kind of realizing that you're 1 step away from the goal, then 2 steps, then 3 steps, then 4 steps, and you're always using your last estimate to update it, so you can be much, much more efficient. If you swept through it the other way, you wouldn't gain anything. So the ordering really matters. And that motivates prioritized sweeping. So prioritized sweeping, the idea is to basically now try and come up with some measure of how important it is to update any state in your MDP. So now we realize, so you can update your states in any order you like, so which states should you update first? Prioritized sweeping basically says, let's just keep a priority queue, let's look at which states are better than others and update in some order that depends on how important we consider that state to update it. And the commonest family of methods basically use the Bellman equation again to try and figure out which of those states is the most important. So the intuition is to say that the states which are changing the most, like if I did my 1-step look ahead, if before my update I thought that the value of this state was 0, then after my update I think the value of this state is 1,000, that's really going to affect all of my computations a lot downstream. So we assume that the magnitude of the error between what we thought before and what we think after, like the change in the Bellman equation, we use that magnitude to guide our selection of which states to do. And we order them by how big the change is going to be. And so this helps us focus on the things which are changing the most. So if we remember going back to this, well, yeah. If you imagine you could have, you could have a situation where you just haven't seen any rewards for a huge part of your state space. You start off estimating the value as 0 for most of your state space. And if it might take you a very, very long time for the actual goal to propagate and start changing all of your 0 values. And in the meanwhile, you don't want to waste time recomputing 0, 0, 0, that 0 is equal to 0 plus 0 each time. So you kind of can ignore the computations in the parts of the state space that don't matter and just focus on the parts that really do matter. Okay, third idea. So is that clear, first of all? I'm going through this slightly quickly, I know. Third idea is real-time dynamic programming. The idea of real-time dynamic programming is to select the states that the agent actually visits. So don't just sweep over everything naively. Actually run an agent in the real world. Collect real samples. These are now random samples from some real trajectory. And update around those real samples. So if an agent is actually, if I'm really wandering around here, I've got some robot and it's really wandering around this bit of carpet, I care much more about those states than what's going on in the far corner of the room, because that's what the agent is actually encountering under its current policy. So you basically use real experience as a guide to seed the dynamic programming and basically help it find interesting states to update. Okay. I really want to mention this slide before we go. So dynamic programming uses full width backups. So what does this mean? It means that when we build these diagrams, when we build these look-ahead diagrams, we're really computing the full width look-ahead. We're considering all actions and maxing over all actions. And then we're considering all successor states that the wind might blow us to. We're considering the whole branching factor of all states that I might get taken to, every single step. We're considering all actions, then all states that we might go to. That's a very expensive process. And so, as a result, and there's a second drawback, which is, in order to do this look ahead, we need to know the dynamics of the system. We need to know where the wind will blow us. We need to know exactly those probabilities. We're doing planning. And so, what we're going to look at in future lectures is how to solve this problem. And the way that we solve this is by sampling. So instead of considering the entire branching factor here, what we're going to do is just sample particular trajectories through this and sample our expectations by basically just, instead of doing a full width search over these things, we're going to just sample a single trajectory. And then in cases where even one backup is too expensive, so we're going to talk about problems later with 10 to the 170 states, you can't even do one iteration of dynamic programming. You can't even do one backup. You can't even compute this for one state. So what do? You sample. So in subsequent lectures, we'll consider sample backups that look like this. We're basically going to start in a state. We're going to sample one action according to our policy. We're going to sample one transition according to our dynamics. And we're just going to do a backup based on that one sample instead of the full branching factor. And that's going to give us a lot more efficiency. It's going to break the curse of dimensionality through sampling. But also it means that because we're sampling the dynamics of the environment, we don't need to know the model of the environment. So this is how we convert from these dynamic programming methods to model-free reinforcement learning methods. By basically, instead of someone telling us the dynamics, we just sample from them. We see what happens. Yeah. Okay. So I just want to point out that contraction mapping is on the lecture notes. And it basically shows you that if you start with any one of these algorithms, that the value function does indeed, value iteration converges to V star, iterative policy evaluation converges to V pi, and policy iteration converges to V star. And the way that all of these work is by the same iterations. They bring your value functions closer and closer together until you find one unique solution, which is the value function in that case. So that's just on the lecture notes. I'm sorry we didn't have time to go through it fully. Okay, thanks everyone.